Hello everybody. So today I will continue with some exercises. Assume that we have the Fourier transform of the function exponential minus absolute value of t, which is given by 2 over 1 plus omega squared. The question is, if we know this Fourier transform pair of the function exponential minus absolute value of t, we are asking for the Fourier transform of d over dt exponential minus absolute value of t. And also we are asking for those function in time, what it should be the respective Fourier transform. So we will use the properties of the Fourier transform in order to get A, B, and C. So I will note fa to be this function, fb to be this function, fc to be the third function. I am giving a hint how could we solve it using the well-established properties of the Fourier transforms. So here I am suggesting to use the differentiation property. It means if ft has capital F of omega as a Fourier transform, so the differential of the function with respect to time will have j omega f of omega. Okay, and here I am proposing the duality property to be used. And in the third question, I am suggesting two possibilities: is the multiplication or the convolution properties of the Fourier transform, because we know already that there is also duality between convolution in time domain and convolution in the frequency domain. So I will note, for instance, f of omega to be the function 2 over 1 plus omega squared. If f of omega equal to 2 over 1 plus omega squared, it means if I will differentiate this function in time, the result will be j omega times f of omega. It means j omega times 2 over 1 plus omega squared. So this is a direct application of the differentiation property of the Fourier transform. Now, we see now the duality. It means this form, this spectrum in F is dependent on omega. So if I will replace omega by time, I will have a function 2 over 1 plus t squared, which is given here, okay, scaled by the factor 1 over 2 pi. So we know from the duality property of the Fourier transform, it means if ft has f of omega as a Fourier transform, it means f now, f if I will replace the omega by the time, it will be 2 pi f of minus omega. So this is what I will apply here in for the function fb, which is this function fb of t, which is 1 over 2 pi 1 plus t squared. So the Fourier transform of 2 over 1 plus t squared, which is this function when I will replace omega by the time, is equal to 2 pi exponential minus omega. It means here I will multiply 2 pi here, and I will replace the arguments by minus omega, but the absolute value of minus omega gives absolute value of omega. Now, if I will divide by 1 over 2 pi, it means I will divide this function by 2 pi, which gives the Fourier transform of fb of t, which is capital FB of omega equal to exponential minus absolute value of omega divided by 2. For the third question, we see this function in time as a product of two functions. It is 1 over 1 plus t squared multiplied by 4 times the cos function, which is cos of 2t. So here I will apply the modulation or the multiplication property of the Fourier transform. So here I know that if I have f1 times f2, it will be 1 over the Fourier transform. The Fourier transform of f1 of t times f2 of t will be 1 over 2 pi f1 of omega convolution with f2 of omega. So here I will split this function as the product of two functions, 4 divided by 1 plus t squared, and f2 will be cos of 2t. So I will calculate the respective Fourier transform of f1 of t and f2 of t. f1 will be this, 4 divided by 1 t squared, and f2 will be cos of 2t. So now what you are seeing in red, it is the Fourier transform of this function, and f2 of omega, which is two terms, which is composed by two terms here, it is the Fourier transform of cos of 2t. Now, I will apply the Fourier transform property of the products. f1 times f2 has, I'm sorry, this is not equality. It means their Fourier transform will be 1 over 2 pi f1 of omega convolution f2 of omega. So this results, it is equal to fc, which is the Fourier transform of fc of t, which is defined by this function. So here I will put 1 over factor of 1 over 2 pi, and I compose the convolution product of f1 and f2. And this is easy in that case to get the results because I am making convolution with a function with the delta function. And you know that convolution of a function with a delta remains the same function evaluated at that argument. And when I will multiply it, I make a convolution of this part with this part, will be the same function evaluated at the argument omega plus 2. And I will not forget, of course, the factor of 1 over 2 pi, which is here. So this is the final results related to item C. It means the Fourier transform of this function, it is equal to this function fc. This is another exercise where we are asking to find the Fourier transform of the function omega t using the properties of the Fourier transform. So this is a time-dependent signal, okay, composed by 3 lines. And we will assume that I have here two constant a and b, both of them positive, with b greater than a. And I will use now the differentiation property to get the Fourier transform. You see here, if you start writing the Fourier transform from the definition, you will integrate functions in the form t exponential minus j omega t. We will see in this exercise that by differentiating the signal, so we will simplify its form until we will arrive to Dirac functions where the Fourier transform is easy to get. And then I can use the differentiation property of the Fourier transform to form the Fourier transform of the function omega t. So now I will start by the differentiation. So this is the original signal omega t. If I will differentiate this signal with respect to time, what I will get? So here we see that we have a line, okay? It is a line. If I will differentiate a line, I will get its slope, and the slope is clear here to be capital A divided by this distance. And this distance, it is exactly this distance, which is b minus a. So this is why you are seeing here a divided by b minus a. It means you have a constant when you move from minus b to minus a. So here we have 0, so this will not be changed from minus infinity to that point. And then I will jump to a constant which is equal to a divided by b minus a. Until I will arrive here, I will differentiate a line, okay? And the line here, you see that this line has a slope negative. So what is this slope? It is this divided by this multiplied by minus 1. Okay, so it is capital A divided by lowercase a. And here we see that after, when we arrive to the point minus a, we will jump to this negative constant until we will arrive here. And this line is parallel to this one. It means they have the same slope. When I will differentiate this line with respect to time, I will get the same thing as here, which is a divided by b minus a. So now this signal, which is called xt, will be differentiated one more time. So here we will have a pulse up of amplitude equal to a minus b minus a at minus b. And here we will jump down. So I will have a Dirac function of a value equal to what? So the value I can calculate it from here. Okay, it means this plus this. It means it is a divided by b minus a. And this distance, it is a divided by a lowercase, okay? Which gives this value. Now, when I will jump here from here to here, I will have the same value here, but with positive sign. And at B, I will have a jump down. So I will have a pulse of the same amplitude, but in the opposite direction. So we will start by calculating the Fourier transform of the signal yt. So yt now, we can write it as a sum of three Dirac functions located at minus b, minus a, plus a, and plus b. And this is what you are seeing here. So we have here 4 terms of the Dirac function delayed by some quantities. And we know that the Fourier transform of the signal yt, which is the second derivative of the original signal, we will note it capital Y of omega. So here, the Fourier transform of delta of t plus b, it is exponential j omega b, and I have a constant here. And the Fourier transform of delta of t minus a, it is exponential. It is exponential of j omega a, and the rest also will be some exponential functions that depend on a and b. So y of omega, it is the Fourier transform of the second derivative of omega, or it is the Fourier transform of the first derivative of x. This is why we write y equal to j omega times x of omega. To get x of omega, so I will divide by j of omega, and I will add a term k delta of omega, okay? But the k here is equal to 0 because the average value of the signal xt is 0. when I will divide y of omega divided by j of omega, I will get x of omega. And x of omega is the Fourier transform of xt, and xt is the first derivative of omega with respect to time. So now I can get the signal, the Fourier transform of omega t, using the results of x of omega, which is the Fourier transform of the first derivative of omega with respect to time. So I can write the Fourier transform of the signal omega t to be x of omega divided by j of omega plus k delta of omega. But I have also an average value equal to 0. This is why I can restrict myself to this term only. It means the Fourier transform of the original signal will be x of omega, which is this term, divided by j of omega, which gives these results. In this problem, we will illustrate an example, the calculation of the output using the Fourier transform of the input and the impulse response of the system. So here we have an electrical network with an input xt and output yt. And we are giving the expressions or the plots of xt and ht. So ht, it is a part of an exponential, of a decaying exponential function. And the x is a simple a step function of terminal value equal to v and a step time equal to 0. Objective is to get the signal yt. So what we have seen before, the output y of an LTI system can be seen as xt convolution with ht. And we have illustrated many examples how can we calculate the convolution products when the expressions in time of xt and ht are determined. Our objective here is to pass through the Fourier transform first. It means transforming, having the Fourier transform of ht and xt first, and then we will get the Fourier transform of y, and then we will apply the inverse Fourier transform to return back to time. So the objective here is to get the output yt using the Fourier transform First of all, I will calculate the Fourier transform of ht. And the ht, it is an exponential function with time positive. So this is why we multiply it by the step function ut. And its Fourier transform is 1 over 1 plus j omega rc. H of omega is the Fourier transform of the impulse response of the system. X of omega is the Fourier transform of a step function of terminal value equal to v. And this gives v times 1 over j of omega, of 1 over j omega plus pi delta of omega. Now, what is the y? The y is the output of our system, and it is the product of h and x. And here we have the product of two functions. So we will have v factor of this rational complex plus this one. Now, our objective is to return back to time, to have y of t. So we have to evaluate the inverse Fourier transform of this term, and we have to evaluate the inverse Fourier transform of this of this term. So I need to decompose this term into two parts. So I will decompose this part as 1 over j omega minus RC divided by 1 plus j omega RC. Plus, okay, plus pi delta of omega. So we did this decomposition in order to recover this term and this term, okay, where the calculation of the inverse Fourier transform is easy. So this term is written as, if I will divide by RC up and down, so I will get this multiplied by V, of course, plus, okay, plus the inverse Fourier transform of this multiplied by V. Okay, so we put the V outside and we calculate the Fourier transform of the remaining terms as indicated here. We know that the step function has a Fourier transform equal to 1 over j omega plus pi delta of omega. And the Fourier transform of the exponential minus t over RC times ut is given by 1 over RC plus j of omega. So here we can say at the end that the output yt, it is a step, which is this step, v times ut. So it is v times ut, and this provides this part multiplied by a sign minus multiplied by v, which gives this one. And this is the plot of yt when a step function is applied. So this is an example where we illustrate the utilization of the Fourier and the inverse Fourier transform to get the solution or the system response of a system when the input and the impulse response are known in time. So here we are considering a nonlinear circuit where we have a source followed by a diode, and here we have a load resistance RL. Okay, so the voltage V1 of T can be seen as a product of the source voltage times Ft, and Ft, it is a train of pulses of that form. Okay, because the diode permits only the positive parts of the signal. So here we will see that when the signal is positive, so the current will go through the diode, okay, and then I will have a voltage here. And between this time and this time, I will not let the diode do not let any signal to pass, so I will have 0. And then I will have a positive shape like this, 0, like this, 0, which is seen here as the voltage V1. So the V1 is the product of Vs times this periodic function Ft. So the V1 is the product of F times the source voltage. So it will be Ft times B cos omega 1 of t, where omega 1 is 2 pi divided by the period t1. So I will split the cos function, cos of omega 1 of t, into two exponential complex. So it is exponential j omega 1 t plus exponential minus j omega 1 t divided by 2. And the voltage V1, the resistance voltage V1 will be split into two terms like this, okay? So we did this in order to be able to get the Fourier transform of V1 in terms of the Fourier transform of Ft. We know that when I will multiply the signal by an exponential function, and I know the Fourier transform of Ft, I will have a delay in the frequency domain. And this is what I have here, the Fourier transform of V1 of t noted capital V1 of omega will be the Fourier transform of this part plus the Fourier transform of this part. So Ft have f of omega as a Fourier transform. When I will multiply it by an exponential, I will have a delay in the frequency domain. And this is one of the properties of the Fourier transform. So here I have a plus, so here I will have minus, and here I have minus, here I will have a plus. Okay? So it means it is sufficient to get the Fourier transform capital F of omega, which is the Fourier transform of this periodic function. We have calculated in the previous videos the Fourier transform of the gate function, and we get it equal to the sinc to a function which is in the form of sine of x by x. Now here I have a periodic function, so the Fourier transform of a periodic function, when this gate function or this generating function is known, will be given by this expression. Okay. So now we will replace A by the amplitude here, which is equal to 1. The period T, which is here, by T1 by 2. And omega 0 by omega 1, which is 2 pi by T1. So at the end, I will have a Fourier transform f of omega, which is a sum from minus infinity to plus infinity of a sinc function multiplied by a delayed pulse. And the delayed pulse is dependent on n, and the n is a variable which is varying from minus infinity to plus infinity. Right. So I have what? I have the sine, I have the sinc function at some specific frequencies, okay? Because it is multiplied by the delta, and the delta is 0 otherwise, it means that this f of omega will exist only at some specific frequencies n omega 1. It means multiple values of the frequency omega 1. Now V1 of omega, it is the product, is given by this expression. So here I will have two terms, of course, and I will also delay the spectrum f of omega by omega 1, and here I will have also a plus of omega 1 in the second term. So this is why I am seeing here two pulses with different delay expressions. And this will be, and I have also to multiply it by b over 2. Okay, so b over 2 times the pi, and then I will have a sine with delta delayed. Okay, so this is the expression of V1 of omega versus V1 of omega, which is the Fourier transform of the voltage across the resistance. Okay, the frequency spectra, so I will calculate amplitude and phase of the Fourier transform, and we see that the sinc function will be 0 when I have n even. Okay, so at 3, 5, 7, 9, so all the term here will be 0. Okay, so if it is 0 and otherwise it is a form of a sine x over x, so sine x over x, okay, which is evaluated at some specific omega. sometimes at some frequencies the value of the transfer, the value of the Fourier transform is positive, and in other frequencies it is negative. So this is why the phase of V1 is equal to pi when the value is positive, and it is equal to minus pi when the value of V1 is negative. Okay? Now I will go to the definition of energy and power spectra densities, and I will start with the energy definition. So all energy signals, what we mean by energy signals, signals that have finite energies. It means that if I will integrate the signal in magnitude here, square dt, under the integral minus infinity plus infinity should be less than plus infinity. It means that the E is finite in this case. If the signal is written in terms of the Fourier transform, it means if I know now the spectrum of f, which is noted f of omega, the inverse Fourier transform of f of omega is given by the following. It means 1 over 2 pi, the integral of the famous expression here. So now the E is defined by the integral minus infinity to plus infinity, okay, amplitude of ft squared dt, okay. So I will leave ft, I can write it ft times ft, and I will replace one of the ft by the inverse Fourier transform expression, okay. Now here I have in one side integration with respect to time, and in the other side I have integration with respect to omega. So I can reverse the order of integration. So I can put here f of omega outside, and I will enter ft inside, and I will also reverse the differential dt by d omega as here. But now if I will evaluate this integral with respect to the differential dt, I am seeing that this part, which is between bracket, it is exactly f of minus omega, okay? So I can say that the E, it is 1 over 2 pi integral minus infinity plus infinity f of omega, and the part which is between the bracket, it is exactly f of minus omega. It means I have this resulting expression in that form. But when f is real, I have f of minus omega equal to f star of omega. It means the complex conjugate of omega. So here f, if I will replace f of minus omega here by f star, so this is the final expression of the E, written as 1 over 2 pi integral minus infinity plus infinity f of omega star f of omega d of omega, okay? And also this will give what? Amplitude square d of omega. So what we have to outline here is that if I have the expression of the signal in time, I can calculate the energy by integrating the ft square dt from minus infinity to plus infinity. And if I have its spectrum f of omega, I can also have the energy in the frequency domain, which is given by this expression, and this is what we call here the Parseval theorem, okay? So since f of omega is a real and an even function, in this case, if we will integrate from minus infinity to plus infinity, will be exactly the 2 times the integral from 0 to plus infinity, okay? So this is why the energy can be written as 1 over pi, which is 2 times this value from 0 instead to plus infinity, as we are seeing here. Okay, so we will define the energy spectral density function of the signal ft as this function only. It means f of omega square amplitude over 1 over pi amplitude square, or 1 over pi f star. Okay, so what is this energy spectral density function? So it is a function which is describing the distribution of the energy over the frequency spectrum. Okay, so I will call EF the energy spectral density function. Okay, but here if I would like to calculate the energy, so the energy will be the integral of the energy spectral density of the function ft.